Okay, perfect. This is chapter 4, based on the 9th edition. All of the lecture slides will continue to be based on the 9th edition, but it turns out that your 7th edition, there is a one-to-one mapping between chapters, and I'll show that to you guys. I'll show the mapping to you after the lecture is done, right? So the materials that are being covered here are in your 7th edition textbook. Some of you have the 9th or the 10th edition. The rest, most of you have the 7th edition. We'll talk about that at the end of this lecture. Okay. Moving on. The last couple of lectures we dealt with motion, right? Inertia, motion, speed, acceleration, and so forth. Now we move to mass. Truth of the matter is we don't know what mass is, right? But not knowing what it is, here's an approximation to whatever it might possibly. The quantity of matter in an object. What is matter? We don't really know what matter is. We kind of intuitively think we know what matter is. Matter is something that has mass. What is mass? It's the amount of matter. Do you see the circularity in a sense?
You don't know what matter is, or nobody knows what matter is?
At a very deep level, nobody knows what matter is. Right? It's typical in science to put labels on things we don't understand, and because we labeled it, we think we understand it. Right? Or we have a superficial level of understanding. It's kind of like Jenna, right? Mm-hmm. Okay. So I'll try to not be politically incorrect, but not being politically incorrect, let's say that I were to take a snapshot of you and then just take the silhouette, right? The outer shape of you. And if I were to draw that on a piece of paper and say, hey, I know Jenna. I know everything there is to know about Jenna because I have the shape that represents her. Is that a true statement that I know everything about you? No. Okay. That's level 1 of understanding. Next level of understanding is to mathematically represent that. Let's say that I can come up with a mathematical expression that can reproduce that outer shape of you, right? The silhouette of you. The fact that I now have mathematically described you means that I know you exhaustively, right?
No.
Not at all, right? So that's level 2 of understanding. Level 3 of understanding of knowledge is now to take a 3-dimensional topograph of you, right? So instead of just a 2-dimensional silhouette, now we have a 3-dimensional, okay, I have to be politically careful. I don't want to be politically incorrect, but like of all the hills and the valleys and so on, right? That's why. So you know topographic maps, right? If you look at the topographic map of the US, you can see the regions that have higher elevation and regions that have lower, like depressions or whatever, right? So similarly, for each person, we can come up with a 3-dimensional representation of the front view, right? That's with all the hills and the valleys and so on. And I can mathematically represent that. If I do so, that mathematical representation is substantially more complex than the representation of your silhouette. Mm-hmm. So now that I have a 3D, if you will, representation of you mathematically, does that mean that I know you exhaustively? Not at all. Science is like this. It's levels. At each level, what happens is we move to a slightly lower degree of ignorance. But the truth of the matter is there is vastly more to you than these mathematical representations, right? And that's true in general. And that's true of matter, for instance. What is matter? I mean, it's very difficult for us to define matter without some degree of circularity. Matter is something that has mass.
No.
What is mass?
No.
Mass is something that matter has, right? So I'm just pointing this. In real life, what happens is we think we know what matter is. You can point to examples. If I say, give me an example of matter, right? You can point to your bottle of Mountain Dew and say that's matter. So now if I have never experienced this, if I was some kind of entity that lives in a universe that has no matter in it, and you try to communicate that to me, there's no way I can comprehend what you are talking about. It's like a person who was born blind. How do you communicate to them the sense of color or even of sight? Let's say that the person who's blind has lived in a society where everybody is blind and you're the one person now who can see. The blind, you tell them that you're able to sense objects. Isn't it amazing that you're able to sense the characteristics of objects that are at a distance from you? The person who's blind can only sense, in a sense, things that are up to an arm's length.
Uh-huh.
To them it's totally amazing that you can experience something that's miles away. Really? How is it possible? It's impossible. Because they have no comprehension of it. So we as human beings are very, very limited in our knowledge. And philosophically, I'll move on, but that opens up an interesting area of philosophy. Okay, having said all of that, we will go on to say that mass is the quantity of matter in an object, right? And we will leave it at that level. But I just want to point out to you that the definition really does not give us very much knowledge or understanding. We think we understand, but we don't really, right? So here it says, it's the measure of the inertia or the sluggishness that an object exhibits in response to an effort made to start it, stop it, deflect it, or change in any way its state of motion. What does it say? What it means is that if my mass is smaller, it's easier for you to push me and make me move. If my mass is larger, it's harder for you to do so. If I have an elephant and a mouse, which is easier to push? The mouse, right? Because the mouse has more matter or less matter? Has less matter / less mass, right? So from a practical, hands-on kind of a sense, we have a feeling for what this is. Okay, weight is the force due to gravity on an object. Students will sometimes mix up weight and mass. Weight is not mass. Weight is a force, right? It is a vector. It has a direction towards the center of the earth, and it's related to the mass, but it's not the mass. Mass is not a vector. Mass is not a force. Kilogram is the unit of mass, right? It's the weight of 1 liter of water at 4 degrees centigrade. So kilogram is a unit, measurement unit of mass. Watch the door, it slams. Thank you.
Does vector mean direction?
Mass has no direction, only weight does.
Right, but you said you used the word vector. Does that mean direction?
Vector means magnitude and direction.
Okay.
Right? So it has a number as well as a direction. So weight, my weight has a number, right? It has a number and it has a direction. So that my weight it's a force that's pulling me towards the center of the earth in that direction, right? So normally, colloquially, we say, like if you were to, I know it's politically incorrect, say to somebody, what's your weight, right? And they say 150 pounds. So people think that is a weight, but colloquially we use it as a weight, but really it's not a weight, it's a mass, right? So to figure out what the weight is in physics terms, in terms of what's the force, you'd have to take the 150 pounds divided by 2.2 to give you kilograms, multiply by 9.8 meters per second square for G to give you a number in newtons, and that is really your weight. But the average person on the street, now this is one of the things that's a bit confusing about a lot of physics, is that physicists have a tendency to use terms that are used colloquially in a different sense. A lot of scientists do this, and they confuse the heck out of lay people. We see this in just about every field of science, using the same terms that are used colloquially to mean one thing and meaning something else. Like we talked about even earlier, we talked about in the previous lecture about fact. Colloquially people say a fact is something that's absolutely certain. I'm absolutely certain that the sun is going to rise, in the east tomorrow morning. But from a scientific viewpoint, scientists in a sense have redefined that term to mean something else. A fact is what I think is a fact today. A group of scientists, competent observers, get together and decide this is a fact that makes it a fact. Tomorrow they come up with another experiment that shows that fact to be wrong, and it's no longer a fact. The new understanding is now a fact. It's very silly, right? Okay, Mademoiselle.
For the kilogram, you said mass of 1 liter of water at 4 degrees
centigrade.
So does it matter what degree it's at?
4 degrees centigrade.
Why does that matter?
Oh, I see. Why does that matter?
Yeah.
What is the matter with... Okay, that's 3 different uses of the word matter, right?
Alright.
No, not at all. Great. I enjoy wordplay like this. The density of water changes as a function of temperature.
Okay.
So 1 liter of water at 100 degrees centigrade weighs a different number than, or has a different mass than, right, yes, than the same at 4 degrees and so on. That's why they specified that. Okay, differentiation between mass and weight. Here's an anvil floating in space, here's an astronaut floating in space. They both have mass. Now let's say that there's no gravitational body near them, no Earth, no solar system, nothing of the sort. They will not experience any force. So what is the weight of this astronaut at that moment? 0. So he's experiencing no weight. The anvil is experiencing no weight. So they have no weight, however they do have mass. So if you try to push this astronaut, you'll find that it's not easy to push him. So if you had a mouse and an elephant floating in space, you would still find it easier to push the mouse than the elephant, even though neither of them has any weight. However, they do have mass. Okay, next we have talked about inertia from a previous lecture, the property of things to change, to resist changes in motion. So if it's stationary, it stays stationary. If it's moving, it stays moving at a constant speed, right? So here is an illustration of inertia. There's a string attached to the ceiling, and from this is a heavy metal ball is hung. There's a hoop, whatever, a loop at each end, right? And you tie a string to the one down here, and you pull the string. Which of these two strings, let's say that the strings are equal in strength, is going to break? Who asked if you're pulling fast or slow? Why did you ask that question? Is it because you read the caption?
Well, yeah, because it depends on what you're going to do. It'll affect the different strings.
Okay. Now, if we didn't read the caption, right? If we were to pull with a certain force here, which of the two of these would you expect to break? The top one. Why?
Mass.
Yes. Because what's happening is the top one is experiencing the weight from this heavy metal in addition to the force that you're applying. So if this is applying 100 newtons and you apply 10 newtons, this string is experiencing only 10 newtons of force. But this one is experiencing the weight of this 100 newtons plus the 10. So this is experiencing a much higher force. So you think that this should break, right? However, due to inertia, if you pull slowly, if you gradually increase the downward force, with a slow increase, the string above would break, which is what you'd expect. However, instead of pulling slowly, if you were to give it a sudden jerk, right? What happens is the bottom string breaks because the inertia of this object tries to keep the ball stationary. So the ball resists the downward motion that you're trying to apply on it. And so this string breaks because of the sudden jerk. Okay, moving on to some more terms. Force, we have said, is a push or a pull. It's an influence that causes an object to accelerate, to start moving if it was stationary, to change its motion if it was already in motion. So force is a push or a pull. Newton are the units of force. You measure force in newtons. 1 newton, symbol is N, is the force that will give an object of mass 1 kilogram and acceleration of 1 meter per second squared. All of these are terms that you probably know from your past, right? You all know what volume is. It's the quantity of space an object occupies. Truth of the matter is, we don't know what space is either. We don't know what it is, why it exists. It's just something that we experience and we take it, if you will, on faith, right? And then we make little building blocks out of that. But having said that, when I make statements like this, I'm speaking from a fundamental philosophical viewpoint, right? I'm not speaking from the viewpoint of science, where in science we assume a lot of things based on faith. We assume that we know this and we just build our little castles based on those blocks of knowledge that we think we have. Okay, so here's an illustration. Here's a boy kicking a ball. He kicks the ball, he applies a force F for force on the ball, and the ball accelerates. It accelerates with an acceleration that's defined by the mass of the ball, m multiplied by a. Its acceleration is equal to the force that he applies. So here is one of the expressions of Newton's laws. Force equals mass multiplied by acceleration. You need to know this. Okay, application here. Here's again a boy trying to push an elephant. The point here is the greater the mass, the greater the force must be for a given acceleration. So Newton's second law of motion basically says the force that you need to apply to get a certain acceleration is equal to that acceleration multiplied by the mass. This is why for a big heavy elephant, it's harder to accelerate the elephant per given force compared to a mouse. So here's Newton's second law. Here's the mathematical statement, F equals ma. That is Newton's second law. Here's the English statement. Notice that one of them has a few more characters than the other, and a bunch more words, right? So notice how the mathematical representation, a lot of people have a tendency to say, oh, math, and freak out, right? But math, well done, is typically a very elegant shorthand notation for what would take pages and pages of words. So here's the English statement of the second law of motion, Newton. The acceleration of an object is directly proportional to the net force acting on the object and is in the direction of the net force and inversely proportional to the mass of the object. It's like a whole bunch of words. What the heck does it mean? This is what it means. right? See how much easier this is to understand? Force equals mass multiplied by acceleration. Now if you place a little arrow on top, force with an arrow on top equals mass multiplied by arrow on the top, that means those are vectors, right? That means the force is in the direction of the acceleration. Next slide. So we've seen that force equals mass multiplied by acceleration, F equals ma. So here we got a block. The force that the hand applies on the brick accelerates the brick on the brick. Okay, now you put 2 bricks, so the mass is twice as much. The same force accelerates the 2 bricks by just half as much. So this is heavier, it's more massive. So for a given force, it accelerates with half the acceleration compared to this. This is intuitive. This is like the mouse, that's the elephant. If you add 3 bricks for the same force, the acceleration is just 1/3 as much. All of them governed by this, F equals ma. So let's say we've got a brick. Now do not do this experiment at home. If you were to drop 1 brick by itself and another 2 bricks tied together, a piece of string, out of the window the next time you happen to be flying, do not do this experiment. Now what happens is, as these 2 bricks fall, is the acceleration on them different or the same? Ignore air resistance. The same. And what is that acceleration? Give me a number.
9.8.
Good job. 9.8 meters per second square, right? Because the assumption is this is over the earth. Unless, I mean, if you want to come up with a different number, you have to show to me that you are actually capable of flying over the moon or something like that, right? If you want to show that you can fly over the moon, you're welcome to bring your cow in. Right? Okay. So, looks like 2.5 of you got that. So, cow jumped over the moon, and so on and so on, right? Okay. So, now, given the fact that the acceleration is the same, is the force on these the same? The acceleration is the same. They're both accelerating with the same acceleration. Is the force on the both of these the same? Nope. To give this a acceleration of g, since its mass is m, you need F divided by m equals g. Since F should be equal to mass multiplied by acceleration, F equals mg. So F by m is g. In this case, we have 2m, right? So the force on this object divided by twice the mass should be still equal to g, which means the force has to be twice as much, which means that for the heavier object, the more massive object, the force with which the earth is pulling the object down, in this case, is twice for this compared to that. So the ratio, for twice the mass, it's twice the force. For 3 times the mass, it'll be 3 times the force. Whatever it takes to keep the ratio a constant, to give you a constant acceleration for the 2 different objects. Okay, defining in term, friction is a resistive force that opposes the motion. If you have a book on your table and you try to push it in a particular direction, what happens is the little roughnesses on the surface of your table, they catch and let go of your book, slowing the book down, right? That is friction. So here's an example. Here's a woman pushing a block, a crate. She is pushing this crate with a certain force, 75 newtons. The frictional force between the block or the crate and the floor is 75 newtons in the opposite direction. In this case, these two exactly cancel each other, right? Which means either if this block was stationary to begin with, as she increases the force, this block has not started moving yet. To have the block move, she would have to provide like 76 newtons or 75.1 newtons, just enough to overcome the friction. If the block were already moving, the block would keep moving and not accelerate. It would move with a constant speed.
So if we're moving towards her, she would run over?
If the block were moving towards her and...
Try to apply force.
Okay, in this picture, if the block were moving towards her, the frictional force would be in the opposite direction. So you couldn't have this situation with the block because the friction is always opposing. Just based on this picture, I can say which direction the block is trying to move or moving. If the friction is in this direction, that means the block must be moving in or trying to move in the opposite direction. Now, if you were to flip this and have the friction in this situation, then you'd have to see what the momentum of the object is and so on. And she could slow it down. So if she doesn't move out of the way, she will get run over. Right? Good question. Extra credit. Okay, definitions. Free fall. We've looked at this. Free fall is basically motion under the influence of gravity. No air resistance, right? You jump out of a plane. Let's say don't do this. There's no air. You'd be under free fall. Terminal speed is in the presence of air resistance. Now, right, you jump out of the plane and what happens is you yank the little cord and parachute opens, right? So as the parachute opens, then what happens is air resistance slows you down until you get to a constant speed falling. Yes, sir.
So without air resistance, even if you had a parachute, it would still be free fall, right?
Good point. Yes. So remember this the next time you happen to be in a plane over the moon. If you jump out of the right, if you try skydiving over the moon, it goes flat.
Okay.
Not as splatty as on the Earth,
Hey, you can
but still
probably
splat.
catch yourself.
Sorry?
You can still probably catch yourself. What's the difference between the moon's gravity and the Earth's gravity?
Good question.
It's pretty significant.
Look it up.
isn't it?
Sorry?
It's pretty significant.
Yeah, there's a significant
To the
difference.
point where if you fell out of an airplane, you'd be fine.
Not that much, no.
Not quite.
1/6 of the gravitational pull.
Okay, extra credit for looking it up. Perfect. So 1/6. So jumping out of a 30-story building on the moon would be the equivalent of jumping out of a 5th-story building on the Earth. The damage to you. You can kill yourself jumping out of a 5th-story building, right? So jumping out of a 5-story building would be like jumping off of a 1-story building. So you could break a leg, and if you hit yourself appropriately, you'd kill yourself. But you could, in principle, jump off. Don't do this off this roof and not kill yourself. Just break various appendages.
Okay.
So the same thing would happen in the moon, like in an object that's like 6 times as high, right? Ish. Okay, that's your first approximation. So terminal speed is because the air resistance slows you down, right? Extra credit for the question and for the input there. So here is an illustration where here's what's happening. We've seen that acceleration is the force divided by the mass. So the force should be the net force divided by the mass. So if there were no air resistance, the net force would just be mass multiplied by gravity, the weight of the object pulling it down. However, if you have air resistance, so here's a person, 2 people, skinny person, chunky person, right? Weight pulling down, air resistance pushing up in both of these cases. What happens now is there's an R, which is the mg, the weight is pulling down, air resistance R is pushing up. So the net force is mg minus R, divide that by the mass to give you the acceleration of this person coming down. It turns out that the air resistance is proportional to the speed with which the object is falling. It's also proportional to the surface area squared and so on. So if you take all of that into account, it turns out that a heavier person will have to be falling faster for the air resistance to cancel out his weight. So terminal speed for the heavier person will be greater than for the lighter person. Okay, so this is illustrating what we have talked about in the past with a feather and a coin. In this case, we all know what stroboscopes are. Stroboscopes, right? Flashing kind of a white light, right? Completely dark room, flash, take a picture, second of darkness, flash, or a millisecond, or whatever, right? A tenth of a second of darkness, then next flash, next picture, next flash, next picture, and so on. So as this ball is dropping, you flash and take a photograph, flash and take a photograph, flash and take a photograph, flash and take a photograph. So you do this for 2 different balls. One of them is styrofoam, the ball on the right, and the one on the left is the golf ball. The golf ball is heavier than the styrofoam ball. So based on this picture, can you tell me, is this experiment being done in air or in vacuum? In air. How can you tell that?
The lighter object.
Because the lighter object is not that one. You're right. The lighter object is falling. It's not accelerating as much as the heavier object, right? So you can see the effects of air resistance here. If you were to do the same thing with a feather and a coin, you'd see this. This would be the coin, that would be the feather. If you were to evacuate this, then they would both fall at the same rate. And you'd see both of these pictures right next to each other. Cool? And that ends the concepts in chapter 4 as per yes.